Okay, so 2.3 is just kind of no slight intended, but the other properties of functions. Not that they're less important, they're just the other ones, right? We've already been talking about some properties of functions such as domain, very good. Whoever did not say that, domain is a property. I'm going to stay on this side of the room. Discontinuities are also properties of functions. So now we're going to look at the other properties of functions, or some of the other properties of functions, and this should be a review, and I know for a fact because my daughter is testing over some of these properties today in her Algebra 2 class, all right? So I know you've seen this before, but it's worth mentioning again, okay? You know that when we review anything in here, it's always a little bit extra spicy review, right? Okay, so we have to tolerate it, and we do that by, eating a lot of spicy foods. I guess it either you get used to it or you get stomach ulcers, okay? Hopefully you don't get stomach ulcers, you just get used to it. All right, so if the graph of a function is doing anything on an open interval. Now, first of all, when we say open interval, we mean what type of interval? X or Y? X. Good. We read a graph like we read a book from cover to, no, that's not right, from left to right. We read it from left to right in increasing order. So the X values are our independent variable. We always read a graph from left to right for increasing values of X. So if a graph is doing anything on an open X interval, it's going to be doing one of these things, either increasing, going uphill, decreasing, going downhill, or hanging out and doing nothing, right? Which means just kind of staying constant. That's going to look like a horizontal line segment. That's it. That's all it can do. Now, there are ways it could go uphill. It could go uphill at a constant rate, increasing rate, or decreasing rate. And it can go downhill also at a constant rate and decreasing, increasing rate, so on and so forth. But right now, we just want to know, is it going up, is it going down, or is it staying flat, right? Cool. So here is a very low resolution image of a function f of x. And we're looking at these x intervals. So notice from x equals a to x equals b, this function is going up. You can eyeball it, right? Ooh, look, it's rising from left to right. We say the function is increasing on that open interval. Then from b to c, it is decreasing. It's going downhill. But notice again, from c to d, it is going back uphill. So these are x values. We say that this is increasing on that interval. Okay? Those are x values. We look for the horizontal locations where the y values go up, where the y values go down, and when they stay the same. Some people want to say that this function is increasing from f of a all the way up to f of b. No, we don't list y values because we're already looking at the y value behavior. They're going up on this x interval, okay? Now, b up here is what we call a stationary point. At the top, you're at the summit, right? So some people might say that at the top right there, at that stationary point, would you say it's increasing, decreasing, or neither? I tend to say neither, right? It's a stationary point, it's a resting point, but some college professors, if you go forward, might argue that it is actually both increasing and decreasing at that same point. In which case, what happens when you have two equal and opposing forces going at each other? Yeah, they cancel each other out. So if you ever meet a guy like that, just nod your head and acquiesce and say, okay, good. Right, and you're trying to make him happy and he's in charge of your grade. Good. So why do I mean that? We are going to be listing open intervals. We are always going to be listing open intervals, which are going to look like this, A, B, not closed intervals, which would, of course, be the beefy brackets on the end. Okay, so I will always ask, what are the open intervals where this is increasing or decreasing? That way we do not have to fight over what's really happening at B. But your college professor that wants it to be increasing and decreasing, he's probably going to insist that you list these intervals with brackets, like that. Okay? In which case, if you did it on the decreasing, notice now you're saying this. It's decreasing at B and increasing at B. You just do what he wants and say, okay. We are going to avoid that argument, and we're just going to say open intervals, right? So we're not going to fight over whether it's increasing or decreasing or both at the top. Got it? Okay, sweet. Again, if we have disjoint intervals, that's non-overlapping. We use the union symbol, which is the mathy word for or. Okay, let's put it to good use here. Let's look at an example of where this is useful. Grandpa George, all right? I use Grandpa George every year. I don't personally have a Grandpa George, but I know Grandpa George because I get to do this problem every year, and I feel like he's part of my family even though he's not. Last period, 3 students actually had a Grandpa George. And we had George Martian here, who is also a George. So his grandkids also have a Grandpa George. Okay? Although he would argue that he doesn't have grandkids yet. Fair enough. Okay? Or kids. Right? Now, Grandpa George in this example is 80 years old. Does anyone here have a Grandpa George? I do. You have a Grandpa George? Sweet. See? There's one in every class. Is he 80? No, he's in his 70s. Okay. So this is not Brett's Grandpa George, but he could be our Grandpa George. He's 80 years old. He's 80 years old, and you know what he's doing? He's sitting in his rocking chair, reminiscing. He's reminiscing about how his weight has fluctuated over his years. Okay? He's rocking back and forth saying, I used to be skinny, and then I was not skinny, and then I got bigger, and then I got even bigger. And then that happened, and then, I lost all that weight. Boy, oh boy. Okay? This is what he envisions in his head. I kid you not. Grandpa George must have been a mathematician or a math teacher because this is what is in his head. He's looking up and to the left, or is it to the right? One of them you're lying, one of them you're reminiscing. And this is what is appearing in his head, in the thought bubble, okay? So, as it says here, while Grandpa George is prodigious at envisioning such graphs in his head and is in his old age, of course that means what, prodigious? He's really good at envisioning such graphs in his head. His knowledge of increasing and decreasing in constant intervals escapes him at age 80. The things the brain can remember and forget when you get older. There was a documentary on the late, great country musician Glenn Campbell. Anyone know Glenn Campbell? Yeah. Awesome musician, okay? The show is called This Is Me, and he had Alzheimer's. But he was a studio musician before he was a solo artist, really, really talented on the guitar. In his Alzheimer years, he actually toured. That's what the show's about. And he could remember any guitar lick and play the guitar without even thinking. Muscle memory just came to him naturally. But because he had Alzheimer's, he couldn't actually remember the words to the songs that he had sung his whole life. So it's kind of weird how the brain works. He can remember how to play the guitar, but he couldn't remember the words to his songs. So it's kind of the same thing here with Grandpa George. He's remembering this technical stuff, but he can't remember, like, where is this graph going up and down? I don't know, right? And so as part of our Rachel Challenge Community Outreach program, we are going to help him. We're going to help him. We're going to help him by defining now the open intervals on which his weight increased and decreased and remained constant. Okay, so here's a first quadrant graph. This is an application. On the x-axis, we're measuring years, and on the y-axis, we're measuring weight in pounds. Okay, we're measuring time in years against weight in pounds, lbs, Libra. All right, so let's go ahead and start by saying W is increasing on, and now y'all can help me out. We're listing open intervals. So from left to right, what's the first open interval where his weight was increasing? 0 to 20? Yeah, 20. Let's drop this line down. Boom, 25. Okay, so we don't say his weight is increasing from 0 to 150, do we? Some people do that, and that's wrong because you're talking about the y values. The y values are going up from 0 to 150, yes, on the x interval from 0 to 25 during the first 25 years of his life. Union, I spy another increasing interval. Where would be the next interval? From 35 to 40. Yeah, 35 to 40, right? Is that it? I said 40, not 40. Now, because there are units here, it's customary to put the units on the back end of interval. So that would be years, all right? We have applications, so units are relevant. Let's go ahead and do the next one. His weight W is decreasing on what open intervals? 40 to 50. Good. 40 to 50. That's it. 40 to 50 years. And then his weight is constant. He had some real consistent years here. His weight is constant on which intervals? 25 to 35. Union 50 to what? 80, his current age, right? Sweet. That's a 30-year span. Way to go. Way to go, Grandpa George. Okay, so we're kind of done with the problem. Is this difficult? No, not really at all, right? But it's kind of fun to think about Grandpa George. It's even more fun now, since you don't know Grandpa George, and it may be unfair to Grandpa George, but he doesn't remember, to infer his biography from this graph. Shall we pause it, I guess? Should we try and figure out what was happening in Grandpa George's life from age 0 to age 80 based upon his weight? He was born at the ripe old age of 0 years, at which time he weighed 0 pounds. Grandpa George is a survivor. Right there from the beginning. Now maybe if you zoomed in, it might be like 5 ounces. He was a preemie. He was definitely a preemie. Well, yeah, that's the cool thing, right? Grandpa George consistently gained weight at an increasing rate. This is not a straight line. It's not a constant rate. He gained weight at an increasing rate up to age 25, consistently. Now look at this. When Grandpa George was 10 years old, he was only 25 pounds. But everyone knew that he came from 0, so, they tolerated him. And look at this. At his high school graduation, when he was 18 years old, he was less than 100 pounds, okay? Yeah. Voted most likely to stay small by his class. But he overcame those odds and that stigma because he got up to his fighting weight of 150 pounds at age 25 and stayed that way for 10 years. So what could have happened maybe from age 25 to 35 where he stayed at 150? What's that? Oh, someone last period said that maybe he became a prize fighter and he was fighting in the 150 weight at age 25, Yeah. Well, yeah, I mean, if you zoomed in, maybe you see some variation, right? But we're zooming out, right? Because, yeah, you every time you eat, you're going to gain weight, to some degree. But he stayed essentially at 150, his fighting weight, in the prime of his life from age 25 to 35. But then something happened at age 35 that caused his weight to spike. He ballooned up to 200 pounds in a 5-year period. What happened? His what? His metabolism, yeah. When you hit 25, guys, when you hit age 25, your metabolism falls dramatically. What else could have happened? His dog died. And he was grieving, so he ate for 5 years? You said his wife died? Maybe his wife and his dog died, and he was grieving. Okay. Someone last period said he quit fighting and got a desk job. Oh, okay. I get that too. Yeah. You have that snack drawer, whatever. All right. So then something happened at age 40. It got his attention, and over the next 10 years, he almost got back down to his fighting weight of 150. What could have happened in his life at 40? What? Oh, he found a love interest who said, "You're at 200 pounds. You're gross to look at." He's like, "You can almost still not see me when I turn sideways." I know. Whatever. He found a love interest, and she was a horrible cook, so he didn't eat her food, and he lost weight. Is that where you're going? Or no? He was trying to lose weight to impress her. Or for health reasons, he's trying to lose weight. He became vegan. He started working more math problems because your brain burns more calories than your body. There you go. And then at age 50, he got back down to about 160. And for the last 30 years, he started boxing again? Maybe so. I was thinking maybe he just joined Das Rec or something. Okay? But he's been pretty consistent for the last 30 years. Now, here's the cool thing about Grandpa George. He's taking great care of himself. He's an ageless wonder. In fact, every year, he's still 80 years old when we get to this problem. So, anyway, there you go. Something fun to think about, right? It's also fun to think about this. Like, this is the water, and there is some weird animal underneath the surface, right? There you go. There you go. This is pre-AP college level math, everybody. Okay. So there you go. There you go. Try to have fun. I guess he would have a fluted tail like that, maybe, and a fin right here. Okay. All right. And a goatee. There you go. All right. Let's do example 2 now. That one was pretty fun and easy. It was fun easy because we had a graph. Now on example 2, we're going to do the same thing, but we don't have a graph. We have equations. So it says for each of the following functions without a calculator, okay, list the open intervals where the function is either increasing, decreasing, or constant, and do it without a calculator. Okay. I guess we're not supposed to use a calculator. Okay. A sketch might help. It might help. It might help. So we are going to sketch these graphs first. And so you might learn some new parent functions today. What do you think the parent function of 3x cubed is? X cubed. Yeah, don't think too hard. That's the parent function. If you have seen him before, great. If you haven't, after today, I expect you to know what he looks like. This is one of my favorite functions. I call him the disco function. Okay? Because he comes in like this, and he approaches the origin like he's going to be a parabola opening down, but then he's like, psych, and he goes up. Okay? It totally is disco, because if you think about John Travolta, right, standing right here, that's what it looks like. And then this piece would come down, and it's like, staying alive, staying alive. Yes, I'm a choreographer in my spare time. Okay? There you go. All right? So that's the disco graph. Now, it also has, at 0, a stationary point. It actually goes horizontal or constant at a single point. Not on an interval, but at a single point. Okay? Its domain is all real numbers. Its range is all real numbers. And we're going to learn this later. It has what we call origin symmetry. If you take that function and put your finger down at the origin and spin it 180 degrees, or just turn your iPad upside down, it looks exactly the same, okay? So now, if we want to sketch our function, 3x cubed, what would the 3 do in front of any function, including this one? Stretch it vertically. So 0 is the y value at the origin, times 3 is still 0, but every other y value is going to be vertically dilated. So it looks like that. And then symmetrically, it looks like this. So the green one is our f of x. It still has a stationary point at the origin. It still goes horizontal, but for a briefer, it comes in a lot more steeper, I guess I should say. All right? So let's go ahead and list, where this function is increasing, decreasing, or constant. So f, in a complete sentence, f is increasing. You can abbreviate increasing inc if you want, okay? Except on test day. F is increasing on, help me out, we read it from left to right. Negative infinity up to 0 would be good, right? It's a stationary point. But because it's a single point, I'm glad you brought up 0. I was trying to draw it to your attention. Because it's a stationary point, you can actually say that it increases through that stationary point. So it's not like the top of the hill, like the vertex, where it goes up and then comes down. That's where the increasing, decreasing behavior changes. This one you could think of as increasing right through a stationary singularity, a single point. So you can actually say negative infinity to infinity. Okay? And of course, then it's never decreasing, never constant on an interval. It's only constant at a point, not an interval. If this function is doing one thing and one thing only, increasing, we would say that it is, f is, we say monotonically monotonic increasing, or we can also say strictly increasing over its domain. They mean the exact same thing. So that might be a vocabulary word. They both mean the exact same thing. Monotonic is like Ben Stein, right? Mono meaning one, like monoceras. They're only allowed to have one sera on their dance team at a time, right? Monotonic means one tone, right? So it's doing one thing and one thing only, going uphill. Strictly would be like your parents. There's only one rule, and it's my rule. Strict. Okay? It's doing one thing and one thing only. It's going uphill. So those are interchangeable over its entire domain. All right, so that's it. That was pretty easy. The graph helps, right? There's your new parent function, x cubed, the disco graph. All right, how much time have we? We have time. Let's do another one. Letter B. G is -5 x minus 4 quantity squared. What's the parent function? X squared. We don't have to draw that because you know what x squared looks like, right? But let's talk about the transformations that we have here. The negative in front of any function is going to do what? Flips it across the x-axis. We really say it's an x-axis reflection. The 5, just like before with the 3, is going to be a vertical stretch. I know, yeah. You're getting ahead. That's good. GT, right? Now, the x minus 4 is inside with the x before we apply the squaring function to it. So that's going to be what? Up, down, left, or right 4? Good. It's right 4. It's on the inside. It's opposite what it appears. It's right 4. So that's going to move the location of the vertex. So because you know what the parent function looks like, we can go straight to sketching this graph. The vertex is going to move over here to 4, 0. And then it's going to open down. And you just have to trust me that this is 5 times steeper than a normal parabola. Okay? That's about the same criteria I'm going to use for yours. The only time we would show the 5, in real steepness is when we're comparing it to another function that's less steep or steeper on the same grid. Like over here, I drew the green one steeper than the purple one. Okay, if you're only drawing one graph, you don't have to worry about how steep it is. Okay, so there it is. That's enough to answer all the questions we want. All right, so now let's go ahead and say that this function g is increasing for what values? -infinity up to 4. Good. This is where some people, for some reason, want to say from -infinity up to 0. But that would be looking at the y values instead of the x values, right? We want to know from left to right. As we come in from the left, like a vertical arm, the graph's going uphill, 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 uphill until we get to 4. And then what's happening to the graph everywhere after 4? Decreasing. So g is decreasing for open interval 4 to infinity. Now, someone last period said, should it be from 4 to -infinity? How would you answer that? No. Right, no. First of all, from 4 to -infinity is not the correct order for an interval. Intervals always have to be from least to greatest. So that person, I won't mention any names, because I don't know all their names yet. No, I do. It was me. Let's just say it was me. Devil's advocate, right? 4 to -infinity, that would be looking at, again, the y values. And we don't do that. We're looking at the y values going down, and we're interested, okay, for what x values does that happen? Starting at x equals 4, everywhere to the right, it's going down, 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 down. And what's happening at 4? Stationary, yeah. You could say it's neither increasing nor decreasing, or you could jump on that weird professor's bandwagon right away. It's both increasing and decreasing. Okay, easy there, right? That was convincing when I role-played that person, right? Ugh. Yeah, so it doesn't really matter. It doesn't really matter. But I want you to list the open intervals, okay? Sweet. That was easy. We got time for one more. Last one. H of x. Oh, last one for just today. We'll do some more tomorrow. What's the parent function here? 1 over x. And we already know what 1 over x looks like. Yes? It's it's this guy. He looks like this and like this. Right? He has the horizontal and vertical asymptote, or maybe it's like that. Yeah. Okay, whatever. Dance move. Too bad that wasn't on camera. 5 times, that could be like the new floss sensation, right? All the kids at baseball games are doing it. I can't do that. I end up like bruising my thighs. All right, so if we pull the 5 out front, it vertically stretches it by a factor of 5. So let's go ahead and sketch it. We'll go straight to it. We're not going to show the vertical stretch by a factor of 5, but the +3 is important because it moves it to the left 3. So we have a vertical asymptote at -3, which you could also get by finding the domain. There's your vertical asymptote. And then it still has a horizontal asymptote here. And, of course, it lived up there in quadrant 1 and 3, so it still kind of lives in this new quadrant 1 and 3, if you will, with the vertical asymptote. All right, so where is this function? We come in from the left. What's the function doing as I come in from the left? Increasing or decreasing? It's decreasing, right? Not very fast, but then it's like, wow! And it goes down forever. It's pretty fast. And then on the other side of -3, what is it doing? Is it increasing? It's also decreasing. It like goes through a wormhole and comes out the top. So AH is decreasing for or on the interval from -infinity up to infinity. Can we step over -3 here? We cannot. We cannot. We have to actually step over -3 because it is not in the what? Domain. Right. You can't say a function is increasing or decreasing where it doesn't exist. Right? I climbed that mountain right there. What mountain? The one right there. There's no mountain there. See, that doesn't make sense. Right? You can't increase where something doesn't exist. Good. So you have to step over it. So it's different than that singularity where the function existed and it was a stationary point where we could include right through it. We have to step over it. So this one actually, it's kind of weird because to the right of -3, the values are bigger than to the left of -3. And you would think if something got bigger, it would have to increase. This function is actually what? Monotonic decreasing over its domain. And that's the power, if not the magic, of a vertical asymptote. Right? So Fitz magic might be over, but vertical asymptote magic is still here. All right, we're done. You can leave a couple of minutes early. We'll pick up there tomorrow with local max, local mins. So have a fantastic rest of your Wednesday.